Ladies and gentlemen, it is your lucky day. Today we're going to talk about logarithms. This is pretty yummy stuff, so I think you'll like it. We're in Chapter 6, Section 3 here, and here it goes. Remember last time we had one of these exponential equations, and we were trying to solve for x right there. So exponentials have a variable exponent. And we said we could kind of sort of make do here and on the calculator find a solution by plotting the exponential graph, plotting the solution 42 here. There's an intersection, and we use the steps to find out that the only place where 42 is equal to 1.25 to the x plus 2.8 is when you put in x equals 2.1661943, whatever. Okay. Um, that works. That's okay. Wouldn't it be nice to have a better way to do that? There is a better way. And what we do is we take these exponential functions and turn them into logarithmic functions. Okay. Now, down at the bottom there, you see that there's this guy called Napier. He lived in the 1600s, and he made up logarithms or discovered logarithms. I don't know if math is created or discovered. That's an interesting philosophical discussion, and you're welcome to think about it. But in 1610, he worked out the logarithms. They were looking for ways to calculate faster and better. And since multiplication is repeated addition and exponents is repeated multiplication, you know, a lot of that brute force work that we just kind of take for granted because we have calculators now, um, was really, starting to get problematic. They had a lot of business flourishing. Ships were going out finding new stuff. There were a whole bunch of things were starting to happen with science and technology and stuff. And so not modern technology like we have, but you know, new things were happening. The Renaissance was beginning to flourish, bloom right about then. So Napier was trying to find a better way to do it. And he made up this word kind of from parts of Latin and Greek, logarithmus. That would be the Latin version of it. Today we just call it a logarithm. It came from the Greek words, two Greek words made a Latin word. Now we just have this weird word left over. Um, Logos is proportion or word is usually gets translated, but it can also point to proportion or ratio. And arithmos, number. So it's kind of a number word. Maybe that's a good name. Maybe it's not. Ratio number might be a literal translation of that, but here's all you got to do. Okay. It's going to look weird, but you just get used to it. It's not a big deal. This is our exponential equation right there. Y equals some base to a power, and that power is a variable x. So, what logarithms allow us to do is to take that logarithm and kind of turn it into that exponential and turn it inside out and to make a log equation, a log function out of it. Okay. Remember when we talked about inverse functions? Exponentials and logarithms are inverse functions of each other. So when you have an exponential function that does this, and you solve it for the other variable and swap the other variables, it is one to one, so we don't have to worry about that and everything. Um, Remember how it mirrored it across that x equals y, y equals x line right there. We end up with this line right there, and that's your logarithmic graph. We just took the exponential graph and turned it into the logarithmic graph. Those are inverses of each other. And so what it kind of means is if we have this, we can turn it into that. Or if we had this, we could take it back into that. They kind of flip-flop, mirror back and forth across that 45-degree line right there. And there's some examples here. These have all numbers. We don't have to worry about the variables or anything here, but we might have an exponential number. 2 raised to the third power equals 8. What we're going to do to make that a logarithm is we're going to say logarithm base 2 of 8 equals 3. You're saying, here's the base, here's the exponent, here's the answer. Okay, and that's what you can see here. Y equals b to the x. Take that x, put it on the ground, equals the logarithm of the base b logarithm of y, like that. So again, we're kind of turning it inside out. We're going to do a bunch of these, but it takes a little bit of practice, but that's what we're trying to do. If I take this one right here, the second one, my base is 3. So the whole trick here is to learn where these parts go and how to move them around. So maybe up here somewhere, if I can find some room, I'll put, this formula. Let's just do it right here underneath. X equals the logarithm. Right here, B stands for the base, and A and Y there. Let's call that the answer. Probably a better name, but and over here where we put X, remember that X is our exponent. So exponent equals logarithm base, the answer. The base is that number that we're raising to a power. X is the power we're raising it to, and Y is the number that comes out of that. Okay. When I write it over here, same thing. This would be my answer equals some base B raised to an exponent. Okay. So they just kind of flip back and forth, and all we're doing is kind of bouncing it to the other side, because now I've got some tricks I can pull over here. If 3 is my base in this problem and 4 is my exponent and 81 is what I get when that happens, then that's see how we just took that logarithmic function, turned it back into an exponential function, and indeed that is what they have right there. If I take this one, the base is 5, the exponent is 2, and when I do 5 squared, the answer is 25. All right. If I take this exponential function right there, there's a 5 squared. So my base is 5. My exponent equals 2, and the answer equals 25. So when I go back from exponential form to logarithmic form, I need to say I've got the log base 5 logarithm of this number, 25, equals 2. Okay, so that's kind of first and foremost. You got to learn how to flip those things back and forth. And let's do a couple more here. I got a whole bunch of them. These ones do have variables in it somewhere, and I think you'll start to see how handy this actually is, because this one's in exponential form right here, and I could come through. If it helps you make that list, by all means. Base, let's just put a B there. How about little b equals 2? I'm taking the number 2, raising it to some power. The exponent is unknown. X, I don't know what that is. So I'm just going to put that like that. Maybe we will put EXP on that. And the answer is 67. So what we're doing here is we're saying, if I need to make a number 67 out of multiplying 2 certain number of times, you can start going through 2, 4, 8, 16, 32, 64, 128. Whoa, we missed it, right? My number is somewhere between 64 and 128. And what that means is that my exponent rather, here, I'm multiplying 2 somewhere. 64 was how many? Let's see, 2, 4, 8, 16, 32, 60. That would be 6 times. 2 to the 6th would be 64. 2 to the 7th would be 128. So I'm somewhere in the middle here, actually closer to the 6 than I am to the 7, right? So it's going to be 6.2 or 3, or, somewhere in there that we're doing. But we can't do any better than that, other than graphing. Right now, the only thing we could do is graph 2 to the x and graph 67 and go get that point, make the calculator do it for us. With logarithms, when I rewrite this, I want base b logarithm of c equals x. So what we want to do right here is to take this. We've already got the base, we've already got the exponent is x, and we've already got the answer. So my base is 2. I would write log base 2 of the answer, 67, equals x. Okay? Right there, do you see what power that does? It gets x all by itself like we want, like we need. Okay, and now all I have to do, and we still got to talk about how to do this, is evaluate the base 2 logarithm of 67 by turning that inside out, making it an exponential equation into a logarithmic equation. I get the x, I isolate the x, and it becomes easier to solve. Okay, this second one is very similar right here, and if it helps you write it out, my base this time is the number that I'm raising to a power, so that's 5. My exponent is x, don't know what that is, and the answer is 165. So when I'm going from b to the x equals c, I need to write log base b. My base was 5, so I'm going to write log base 5 of c, of the answer. Maybe we should put a c here like that. Um, so of 165 equals the exponent. Okay. Again, we have isolated x. It's all by itself. All we have to do now is evaluate the logarithm over there. Your calculator will do some of those, many of those, but we'll get to that. Let's do this one right here. This is an exponential. I have base b is b. I don't know what it is. So this time we're looking for b, trying to figure out what that is. The exponent is 7, and the answer, they're calling it c. I'll switch over to c because that's less to write, would be 23. So I need to write log base b of 23 equals 7. In every case, you're kind of taking the base and putting it there, and the exponent and putting it over there, and the answer and putting it there. Okay? And if you can just kind of hang on to that and say, I don't know how Mr. Napier came up with this, but it works, so I'm going to ride with it for a moment and see if I can get to where I understand it. Let's go back the other way. Here are some logarithms on the bottom. We'd like to turn them into exponentials. We know this is the base b. We know this is the exponent. We know this is c. So if I've got log base b of c equals x, I can turn it back into b to the x equals c. My base is 10. My exponent's over here, x, and that's going to be 137. Okay. Again, this still doesn't really answer the question of what these values are, but I can start to get a feel for what they are. I know that 10 to the first is 10, and 10 to the second is 100. That'd be 10 times 10, 100. And see how I'm looking for a number that fits in between those. 137, somewhere there in the middle. So I'm going to need something like 10 to raise to the 1.4 or something like that. I can start to kind of interpolate and get in between 10 and 100 and say, okay, I got to be in between 1 and 2 when this happens. Uh, so that's kind of a good thing to start building right there. Here again, here's another one. The base is 6. The exponent's over here, 8. And when you raise 6 to the 8th power, that's a c. That one we probably could get our hands on. 6 times 6 times 6 times 6. There's 4 of them, 5 of them, 6 of them, 7 of them, 8 of them. And we could start multiplying these things out. Of course, your calculator will give you a number for that too. But, that's going to be a pretty big number. But changing this logarithm where it was kind of locked up in the middle there to an exponential form means that I can get to that variable that I need. All right, one more here on this page. We've got the base raised to a power, b to the 4th equals the answer, 112, c. Okay, And then we could take the fourth root of both sides and get b, right? So these are just kind of ways to sneak up on the answer, change it to the other form, and you got a handle on how to solve that thing. All right. Of course, we'll do a bunch of these in class too, and so we'll see more. Right here, I have some that we can do even before we learn about how to do these on the calculator. Um, some more practice changing these things from but back and forth between exponentials and logarithms. So this is good practice here too. If I have this guy, 3 to the x equals 27. If I change that from this exponential form to a logarithm, and very often this is a good trick. If it's in exponential, probably want to go log. Over here, this is the log equation. Might be useful to go to an exponential equation. Okay, so that's always an option. There are other tricks we're going to learn here eventually, but let's try that. Let's go to a log form on this thing. What I'd have to do is I'd say log base 3 of 27 equals x. So we've got that. Okay. Well, maybe we can't really see our way through what that means. Maybe this one it's better to take 3 and start multiplying it and see if we can find a number x that'll give us a 27. So if I take 3, that's just 3. Multiply with another 3. 3 times 3 would be 9. Do it one more time. 3. Oh, there's a 27. Right? See how 3 to the third would give me 27. So that number we were looking for, x, would have to be that 3 right here. Here is a similar kind of problem. A base 6 logarithm of the square root of x equals some number. I don't know, man. Let's try going to exponential form. I've got the base 6 raised to the exponent x equals the square root of 6. And you go, hey, wait a minute. If x was 1/2, that would be another way to write the square root. So in this case, x is 1/2, and we actually found that one. Uh, so that's good. Here's b cubed equals 64. Going to a logarithm may help, may not help. It would look like this: log base b, the number that I'm raising to a power, of 64 equals 3. Well, I don't think that really helped in this case. Um, if I were trying to solve this problem for real, I'd say I've got b to the third equals 64, and I'd slip in here and take the cube root of both sides. And then the cube root and the cube would cancel each other, and I would have b equals the cube root of 64. I could come over to my calculator, hit the math button, go down to the cube root, number 4. If you want x root, it's number 5. But here, and you could do it that way. But I just want to do the cube root. That's built in. Of 64 is 4.0207, whatever. Okay. So we could get an answer out of that. Down there on the bottom, we've got this log function. The base is 10, the exponent is 6, so that would be 10 to the x equals 10,000. Okay? Well, I know that every time I multiply by 10, it's going to move the decimal place, so I'm starting it right there. And, well, actually, yeah. To get 10,000, I would have to multiply 10 times 10 times 10 times 10. Right there. The first two would give me 100. Next one would give me 1,000. There's a 10,000 right there. So I need to multiply 10 4 times. X would be equal to that 4 to make that work. Okay? And going from logarithmic form to exponential form helps me to get there. The base is 8, the power is 2, so 8 squared equals some number c. 8 squared is 64. Okay. So sometimes you want to go one way, sometimes the other. It just depends on what you've got. Here on this one, I would have b to the 5th power, base to the power equals 32. And you go, huh, I know 32 is a power of 2. Would that work? If I took 2, multiplied it 5 times, there'd be 4, 8, 16, 32. Sure enough. Okay. B would have to be 2 there. That is a base 2 logarithm that would do that. So those are pretty handy. And I want to show you this calculator. Oh man, I left that dumb calculator there again. I'm going to go ahead and finish this, and I'll go back and look see how messed up it was. The controls are on one screen, and my is showing the other one, so I kind of get in this trap and do it myself. I'll finish this up and see if this is maybe I got to redo it. You can use any base you want. Base 6, base 2, base 4, base 17. Anything that you want to raise to a power works. But your calculator only has two bases on it. It's got base 10 and it's got base E. Base 10 is called the common log. Base E is the natural log. And here on the calculator, you can see that 10 to the x, that would be my base 10 exponential equation. Whereas when I hit the log button, that's going to be understood to be a base 10 log. And then here I've got e to the x. So this would be the logarithmic in naturale, the natural log of a number. Okay. So we always try to shuffle off to the base 10 or the base E simply because those are the two that I have on my calculator. All right. So when I'm looking at this one right here, then, 10 to some power is 67. I don't know. That's exponential. Let's go to logarithm. So I'd write log base 10 of 67 equals x. And I've got a button on my calculator. There's a base 10 log. All I have to do, and remember this was, I think we looked at one like this before. 67 is in between 100, which would be 10 to the second, and 10, which would be 10 to the first. So I better be somewhere in here in the middle, 1.456, somewhere in there for this to work out. But all I have to do to get it is hit logarithm 67. And there it is, 1.826 something. Okay. So that's pretty handy. If it looks like this and it's log 137, that's a logarithmic equation. But if they don't specify in another base, it's understood to be 10, like that. So you want the base 10 log of 137, hit your log button. 137 is 2.1367. Okay, raise 10 to the power, and you could go back the other way. Here's my 10 to the x, it's in yellow, so hit the yellow button, hit the 10 to the x button, and put in 2.1367. I rounded a little bit here, so this is going to come off a little bit more or less than 137. That's pretty close, right? So that's okay. Down here on the bottom, I have an exponential, and if I write that in log format, I've got the log base E of 165 equals x. Well, this log base E is what we call the natural log. So I've got the variable by itself. I can come in here and hit natural log 165, and it will go get that number for me. It's 5.10594, blah, blah, blah. Okay. You take this number E, right, to the 5.1. Let's just chop it off there. E, remember, was 2.7181. This goes on forever. But if I raise that to the 5.10595, then I'm going to get 165, except for the two places that I've already rounded this thing off and messed it up. I'll try it real quick here. 2.718 raised to the 5.10595. 10595. Okay, again, we've rounded, so it's going to come off a little bit different, but 1.64.9. We're pretty dang close. All right. Here is a natural log. This is a logarithmic function. Natural log has a base of e. So what I'm really saying here is base to the power, e to the 8 equals c. And you want to do that on the calculator. There's your e to some power. It's in yellow. Hit the yellow button, e to the 8. And that's going to be 2,981, a little bit short of that. Okay. So those aren't too bad once you get the hang of where everything's got to go. Base 10, we like. Base E, we like. Everything else, we've got to do something different. I'm going to show you that another day. But here is the final little screen on this thing. Let's rip through these real quick. Here's a logarithm. It doesn't have a base specified, so it's understood to be 10. And I could rewrite this 10 to the x equals 6237. Okay, that's not going to move me closer to the answer. What will move me closer to the answer is hitting log 6237. You want to take the number 10, raise it to some power. That power is going to have to be 3.79 stuff. Okay. The one just below it, 10 to the x equals 67. I got to get at that x all by itself, right? Let's change this one to a base 10 logarithm of 67 equals x. Of course, I don't have to write the base 10. If it's 10, then it's understood to be 10. And all I have to do is take my calculator and go log 67. And there's that 1.826. I think we've seen that a couple times now. Some of these keep sneaking back in. Right here's a natural log function. The base is understood to be e. I don't need to put it if it says ln. It's understood to be e. But e to the 8th is the number I'm looking for. I've got e to the something on my calculator, so go second e to the x. The exponent is 8 in this case, and that's that 2980. Are these the same problems we just did? I gotta see this. Uh, some of them are, some of them are not. Or they are, and they're in different orders or something. Okay. Anyway, that's enough of that. I got to go teach another class. Thanks for stopping by. I'm probably going to re-record this, but we'll see. Bring your questions. Have a great day. Thanks.